Hello everyone. Today is our seventh interactive session on circular dichroism and Mossbauer spectroscopy. So, in the last lecture, we were discussing about the protein structures and how we can determine the protein structure, especially secondary structure of protein, using circular dichroism. So, I hope it's been clear to you by now, but I'll be summarizing it for like 2 to 3 minutes again, and then we will be moving to a discussion of some examples like applications of circular dichroism. This will be the last session on the circular dichroism part. We will be wrapping up today on the circular dichroism, and from the next session onwards, we will discuss Mossbauer spectroscopy. And if you have any doubts, you can write in the discussion forum. And since from last few lectures, I see a decrease in the number of students attending these interactive sessions, so I request you to participate as much as you can. So let's begin with our today's session. So just we will revise it again. That is, light is an electromagnetic radiation which has its both electric field and magnetic field vectors associated perpendicular to each other. For example, when we are recording a UV visible absorption spectra, so there we don't need a plain polarized light, or we can say there we use lights which has its electric field and magnetic field vector rotating in like vibrating in all directions. So here, this is the electric field vector. If you this is the electric field vector, and magnetic field vector, which is a weak field, is associated perpendicular to the electric field. So in case of uh, recording in case of recording a CD spectra, we will require a plain polarized light. So how are we gonna get this plain polarized light? So firstly, if we take an unpolarized light, a normal monochromatic light which has its vibrations along all the directions, as you can see from the arrows in this part. So this is unpolarized light with its uh, electric field and magnetic field vectors vibrating in all possible directions. So when we pass it through a polarizer, this polarizer will allow only light passing through a single plane, which is parallel to this polarizer. So here we as a result we will get a plain polarized light. Now, if this plane polarized light is passed through a chiral molecule, then this chiral molecule can rotate this plane polarized light either in a right hand direction, or we can say like clockwise direction and anti-clockwise direction. So here we will get a right hand and left hand rotated light, which we call, this phenomena is called optical rotation, and the rotation of angle and the angle at which the light is rotated is called optical rotation angle. So if this chiral molecule, we know, if a generally chiral molecules might have in different enantiomers, uh, which are like uh, which are like mirror images of each other but are not superimposable on each other, that is mirror image and non superimposable on each other. So for if this chiral molecule has two enantiomers, enantiomer A and enantiomer B. So if enantiomer A rotates the light anti-clockwise and enantiomer B rotates the light clockwise at the same optical rotation angle but in different directions, so we can say that the chiral environment can detect the this chiral molecule can detect this plane polarized light. Now this consists two part, that is right hand light which is rotated right hand side and light which is rotated left hand side. So this consists of two parts where when these right hand circularly polarized light and left hand circularly polarized light. So here what we are considering two parts, that is in case of circular dichroism we consider circularly polarized light. So plane polarized light is this. It's but in the case of circularly polarized light, if you see uh, the plane polarized light, right hand and left hand, these are associated at 90-degree angle with respect to each other. So, circular dichroism is differential absorption of this right hand and left hand circularly polarized light by an optically active molecule. A linearly polarized light is light with oscillations confined to single plane, but the circularly polarized consists of two perpendicular electromagnetic planes, plane waves of equal amplitude, which are at 90-degree difference in like uh, which are associated at 90-degree phase angle with respect to each other. So in this case, in the case of circularly polarized light, we have now two planes which are associated at 90-degree with respect to each other. And this circularly polarized light can rotate in one of the two possible senses, that is clockwise and anti-clockwise, as already we have discussed. So this is the basic we were discussing. You can see that this circularly polarized light in both the cases, in this case it is clockwise and in this case it is anti-clockwise. So these are rotating uh, perpendicular to the direction of propagation. Now this right hand circularly polarized light and left hand circularly polarized light are non superimposable. As you can see that this is, if this is moving clockwise and I mention it as RCP, and this is moving anti-clockwise and I mention it as LCP. So if you see, these are mirror image of each other, and if we superimpose like both of them on each other, then we will see that these are non superimposable. So chiral molecules can detect the difference between these right hand circularly polarized light and left hand circularly polarized light. Now, there are two cases which arise of this RCP and LCP when passed through a chiral sample. So, first is these right hand and left hand circularly polarized light can move at different speeds through the sample. That is, one is moving faster than the other, and the second case is that one of them is absorbed more than the other part. That is, if we can say that right hand circularly polarized light is absorbed more by the chiral sample than the left hand circularly polarized light. So there are two parts. First is which depends on the speed at which both the lights are moving, and the other part is the differential absorption of both right hand and left hand circularly polarized lights. So the phenomena which generates out of this differential speed of moving of both these lights is called optical rotation, and the effect we call is circular bifringence. And the second case, where both are absorbed differentially, this this results in uh, ellipticity, that is the differential absorption of both the lights, and the phenomena in this case is ellipticity. So for the speed, the phenomena is optical rotation, and for the differential absorption, the phenomena is ellipticity. And this optical rotation part, this depends on the speed of light, and the speed of light, it uh, it hints towards that it depends on the differential refractive index of the sample. Like for example, we have a sample and it has a refractive index of its own, but the light, both the lights, one of them passes through it more fastly and the other one passes through it slowly. So it depends on this refractive index of the sample. And the this phenomena, what we call this optical rotation, this sorry, this optical rotation part, and the second part, that is differential absorption, is what we call circular dichroism. This is optical rotation dispersion. And the and from here we get the, based on the differential absorption, we get the circular dichroism phenomena. So it depends on the difference in the uh, left absorption of left hand circularly polarized light and right hand circularly polarized light. This we have already discussed. So now, origin of this optical activity. So we have already discussed about the this Schrodinger equation, and how the perturbations in the system leads to different transitions, and how electronic transitions take place in a molecule. So if we this transition moment integral tells us about the probability of transition of electron from its ground state to excited state. So if we irradiate it with an electromagnetic radiation of certain frequency, and and we see whether this molecule will absorb the light and will be excited or not, it depends on this transition moment integral. And this transition moment integral has its psi function in the excited state and the its psi function in the ground state. So this operator is what the change we are introducing in the system. That is, in this case, we are irradiating it with a light, and this light has now it this dipole moment. This O is dipole moment operator in this case, and it is of three types: electric dipole moment, magnetic dipole moment, and electrical quadrupole moment. Electrical dipole moment is the is the dominating part, which plays the main role of this excitation. If and the magnetic dipole moment is a weak field effect, so it doesn't it its role is lesser than the electrical dipole moment. And this electrical quadrupole moment is very negligible, so we don't consider it in this transition moment integral calculation. Now, electrical dipole moment, this is the electric dipole moment vector, okay? And this electrical dipole moment interacts along the position vector, that is xyg axis, that is along a line. It is dependent on the position vector. So, in the direction which the uh, in which the change in the electronic distribution is taking place. So if we represent it like this is the representation for the electric dipole moment and how it acts. So it can be x, y, or g position vector. Okay. And if we consider this magnetic dipole moment, this magnetic dipole moment is a cross product of position vector and momentum vector, and it operates perpendicular to the position vector and moves or interacts in a circular way. That is, it acts perpendicular to the this electric dipole moment and moves in the circular manner. So, in the cases when we record this absorption spectra, there only electronic distribution of a molecule is involved, and that's why there we consider only the electric dipole moment factor. That is, it impacts the absorbance by a sample. And this is the equation we get from Beers-Lambert's law. A is equal to epsilon Cl, where epsilon is the molar extinction coefficient, and it is the intrinsic molecular property. Uh, but for but for a but to record the CD spectra for a molecule, we need to have this both electric field vector and magnetic field vector. Both should be active. Now, this magnetic field vector is the rotational strength of molecule. So, in the case where both are active, we call it rotatory strength of the molecule. Here, it was the oscillatory strength of the molecule, that is, the oscillation of electrons in a molecule, and this magnetic field was associated with the rotation of the electrons in the molecule. But here, in the case of but in the case when both are involved, there we call it a rotatory strength. Now, if we see when this electric if, when we see that this electric dipole moment and magnetic dipole moment both are active, so here this results into a helical motion. Both combines electric dipole moment and magnetic dipole moment combines to form a helical motion. And we know our right hand circularly polarized light and left hand circularly polarized light moves in a helical motion. So this is also this generates this helical motion. So in the molecule where both the electric dipole moment and magnetic dipole moment is active, there we will get a helical motion. So that is the reason only the molecules where this both of these are active will be able to interact with the helical motion of the right hand and left hand circularly polarized lights. So now we need to find out which are the molecules where we will get both of these active. So what kind of molecules have these two active? So electric field vector, as we have discussed, depends on the position vector xyg, and magnetic dipole moment vector depends on the this rotational strength of the molecule, which is rx, ry, and rg vectors. So we have to find out the molecules where both of these are active, such that X and Rx, Y and Ry, Z and Rz, each of them are associated in the associated in the molecule and are active together. So, so we know now the molecules, that is the chiral molecules, will only be able to detect these light, right hand and left hand circularly polarized lights. So, firstly, we will see the optical activity. That is, it will rotate the plane polarized light. And these molecules are mirror image of each other but non-superimposable. Now, molecule belonging to point group CN and DN are optically active as they don't possess a center of symmetry and plane of reflection. If I show you, so for chirality, we looked into the symmetry elements in a molecule, and based on their grouping, considering some mathematical rules, we classified molecules. Uh, we classified these molecules into point groups. Now, what were the symmetry elements we have discussed? Identity operator, rotational proper axis of rotation, plane of symmetry, and improper axis of rotation. So these are and also inversion center. So these are five type of symmetry elements which we have to find in a particular molecule. uh, so Cn can be n greater than equal to 1, and this plane of symmetry is of three types: horizontal plane, vertical plane, and dihedral plane. Now this Sn, if we say n is equal to 1, then it means that the molecule just have plane of symmetry. So if a molecule has plane of symmetry, that means it is achiral. And S2, and this S2 improper axis of rotation is equal to inversion center, meaning that if a molecule has this S1 S2 and also improper axis of rotation with n greater than 2, then the molecule will be achiral. So we found out that all the molecules have this improper axis of rotation present, like most of the point groups. There were only two point groups, that is Cn and Dn point group, in which this improper axis of rotation is absent, and we can say that that plane of symmetry Sorry, there were only two point groups, Cn and Dn, which have this improper axis of rotation absent, and therefore we call Cn and Dn point groups as chiral groups. So in the last class, we also discussed some examples of how to find out the symmetry elements and point groups. Although in the beginning lectures we discussed about this, how to find the symmetry elements and point group, but these were the examples, and we connected these examples with the chirality in that particular molecule. So firstly, you have to find out the symmetry elements, then associate it with the point group, uh, like classify based on those symmetry elements. Into a point group. So in a point group, if you look for the character table of a point group, then in the fourth column, which belongs to linear and rotational functions, you have to find out whether in the irreducible representation. In the first column, we represent the irreducible representation. So for the more detailed explanation, follow the interactive session 6. There I have like discussed it in proper details. So these are irreducible representation in the first column. So in the fourth column, you have to see whether the position vector and the corresponding rotational vector in this directed towards the same position vector is associated with the same irreducible representation. If that is the case, for example, in this example, Z and RG are allotted to the same irreducible representation, that is B1, Y and RY to B2. So we can say that this molecule has both electric field and electric dipole moment and magnetic dipole moment active together. So this is this molecule is CD active. So look into the examples, and this is the instrumentation we have already discussed. That is, we take a light source which has its vibrations in all the directions, and this light source consists of the light in full wavelength region. So white light, if we consider, that is, it contains all the possible uh, light in all wavelength region. So we will pass it through a monochromator so that we get a light at a which absorbs at a particular wavelength. So let's say if it absorbs at 650 nanometer, and that light is still has its vibrations in all possible directions, as you can see in this part. This monochromatic light has also its vibrations in all possible directions. So if we pass it through a polarizer, which will give us a plane polarized light, that is light which has its plane in only which has its vibration in a single plane. Now we pass it through a PEM, a photoelastic modulator, which will introduce a rotation in this plane polarized light. So this plane polarized light is now converted to right hand and left hand circularly polarized light. So now we have two planes which are associated at 90-degree angle with respect to each other, and this right hand and left hand circularly light is passed through the sample, whether chiral or achiral, and the result and the in, and the transmitted light is then detected by the detector. So this photoelastic modulator converts the linearly polarized light into circularly polarized light. So when we have to record the circular dichroism spectra for a molecule, we firstly record the absorption spectra for the molecule. because CD spectra gives a signal only when the molecule species is optically active. That is, there is a symmetry in the molecule. And CD uses left and right hand circularly polarized, and we record the difference in the extinction coefficients of the both the parts of the light. So if in the sample we have two enantiomers, let's say enantiomer A and enantiomer B, and if enantiomer A gives us a positive band in the CD spectra and enantiomer B gives us the negative band. Uh, and remember, the absorption spectra doesn't define whether the molecule is chiral or not. Absorption spectra depends on the electronic transitions, that is, it will depend on the like n to pi star transition, sigma to sigma star transition, pi to pi star transition, what kind of electronic transition involved in the molecule. But CD spectra defines us whether the molecule is chiral or achiral. So for example, if we record the absorption spectra, and this is the absorption spectra we get. So we have three bands in this absorption spectra. Band 1, this small intensity band, and the third band is at higher wavelength with greater intensity. So for the same molecule, if we record the CD spectra, we will uh, we will not get the we will see that we will get only two bands, that is bands corresponded to second and third absorption bands in the absorption spectra, which means that the second and third bands are coming because of the chiral part of the molecule, the chiral part in the sample. So this shows that the molecule is chiral, and for the molecule, for the part which is chiral, we are getting a CD spectra, but this part is achiral. Now, CD spectroscopy is used to study protein structure. So, primary structure is basically dependent on the sequence in which different amino acids are present in a chain. So, primary structure tell us about the linear sequence of amino acids. So we can get the information about primary structure of protein from the from its sequencing, like which amino acids are associated, whether like A, C, T, G, adenine, cytosine, thymine, this guanine. So what is the sequence of the amino acids present in that particular protein? Now coming to the secondary structure of the protein. So hydrogen bonding between this carbonyl and amine part plays a huge role in the secondary structure. So uh, there is a hydrogen bonding present between the oxygen and nitrogen, oxygen of the carbonyl bond and nitrogen of the amine bond. So there is hydrogen bonding between these two, internal hydrogen bonding, and we can say because of this hydrogen bonding between C double bond O and NH moiety, it leads to the folding of protein into two different structures, that is alpha helix structure and beta sheet secondary structure. So there are two secondary structures here, which results out of the hydrogen bonding in the protein, that is alpha helix and beta sheet. So there is this mistake I have done here. The secondary structure of protein defines the alpha helix structure of protein and alpha helix and beta sheet. And this in this bond, if you see, so secondary structure, I'm drawing it over here. NH, NH2, amino acid 1, carbonyl. This is amide bond peptide, amino acid 2. So if you see, this is the primary structure of the molecule of the protein with the N terminal and C terminal. And there are different amino acids part of this chain. So the sequence which defines this gives us the primary structure. Okay. Now coming to the secondary structure. So the secondary structure results out of the hydrogen bonding between these C double bond O and NH moieties. Okay. And the secondary structure, this hydrogen bonding between C double bond O and NH leads to folding of proteins into alpha helix secondary structure and beta sheet secondary structure. So alpha helix has helical structure and the side chain of amino acids in this part remain outwards out of this helical structure. And these amino acids, chiral amino acids, introduce chirality in the alpha helix structure. Induced chirality. So if you see, let's say the NH bond of from here is doing a hydrogen bonding. Hydrogen of this NH NH bond is doing a hydrogen bonding with the C double bond O oxygen. So this is how hydrogen bonding is present in this alpha helix secondary structure and leads to the helical structure of this protein chain. So here all peptide bonds except first and last participates in hydrogen bonding. So make sure, remember it clearly, that the primary structure is just about the sequencing of the amino acids which are forming the protein chain, and the secondary structure is mainly dependent on the hydrogen bonding between the protein chains. So in the case of alpha helix secondary structure, we get this hydrogen bonding internally within the this spiral structure. But in the case of beta sheet, hydrogen bonding is present between two different or same polypeptide chains, and it is represented like this. Okay, and these beta sheets are of two types. So beta sheet is of two types: parallel and anti-parallel. So here there can be two types also, like same kind of polypeptide chains are arranged in parallel or anti-parallel manner, or there are two different polypeptide chains which are arranged in parallel or anti-parallel manner. So what happens in the parallel chain? We have a polypeptide chain. So this polypeptide chain N terminal, and this is C terminal of a polypeptide chain. So here we have same or different kind of polypeptide chains whose N and C terminal are parallel to each other. Okay, this is the parallel beta sheet type. But when the N and C terminal of a polypeptide chain is opposite to each other, then we call it a anti-parallel beta sheet. Okay, so this was about the secondary structure of the protein. So there was a mistake in this slide which I taught in the last session. So I'll update the presentation like PPT slides for the for today's lecture, and please follow this session. Okay. So now coming to the tertiary structure of the protein. So in the case of tertiary structure, we look into the arrangement of protein in 3D space. For example, we have alpha helix secondary structure, then we have a beta sheet structure, and again alpha helix structure. So we are now looking into the 3D 3D structure of the protein chains. And this tertiary structure also involve other interaction. Tertiary structure involves other interactions also. So secondary structure we were discussing about the hydrogen bonding. But in the case of tertiary structure, we will have hydrogen bonding, then disulfide bond, hydrophobic structure, hydrophobic interaction if we say, or any ionic bonding. And the quaternary structure generates by interaction of different tertiary structures to form dimers, trimers, tetramers, etc. So now the question is, how circular dichroism is important in determining the protein structure. So we can easily determine the secondary structure of a protein with the help of a CD spectra. So if you see this graph, which is psi versus wavelength of the light. So if we have a alpha helix structure, we will get three bands. We will get a positive band at 193 nanometer, and uh, two negative bands at 218 and 222 nanometer. So if you are recording a CD spectra for a protein and you get this type of uh, this kind of spectra with the positive and two negative bands, so you can easily define it as the protein with alpha helix secondary structure. And also for the beta sheet, you will get a positive band at a higher wavelength, like almost 2 to 3 nanometer more than the alpha helix positive band, that is at 195 nanometer, and a broad negative band, single broad negative band. So this is the uh, key band which will help you in differentiating between the alpha helix and beta sheet of the structure. Now you can have a random coil structure also. So for that you will get a negative band and no band in the positive side. So this is how you can differentiate uh, between the structure of the protein. And also if you take a protein and it is getting like it is uh, its structure is getting deformed with respect to the change in temperature or change in pH. For example, it is moving from beta sheet to alpha helix. Sorry, if we say that it is moving from a random coil to beta sheet to alpha helix, you will see the changes in the bands. That is, certain bands will disappear and different bands will appear in the CD spectra. And for this, the spectra needs to be recorded in the far UV region, that is down to 190 to 170 nanometer. This we have already discussed. So this is the same case as I mentioned, that with the change in pH, that is with the change in pH from 5.9 to 12, the protein sample is changing its structure from beta sheet to the alpha helix form. So here you will see that the broad band which was present earlier in the CD spectra is now forming two different bands in the negative size side. So you can define that a protein is changing its structure from beta sheet to alpha helix. So these are the values which I have taken from the reported literature. You can follow this, and this is the summary we have discussed. That CD spectrum is sensitive to the secondary structure change, and for this we record a CD spectra in the far UV region, that is 170 to somewhat about 250 nanometer. And the secondary structure types are alpha helix, beta turn, random coil. And for the tertiary structure, we look in. And the CD spectrum is also sensitive to the tertiary structure change, which is based on the aromatic groups in some of the amino acids. For example, amino acids such as phenylalanine, tyrosine, tryptophan, and disulfide bonds also, as I have discussed in the last few slides, that the tertiary structure involves other interactions such as hydrogen bond, disulfide bond, hydrophobic interaction, and ionic bonds also. So this was about a brief summary of the last lecture, and I just wanted to uh, be clear about this. I wanted you guys to be clear on the structure part and how why we are recording the CD spectra and some of the basics. So now we have almost covered all the part, that is how CD spectroscopy generates, We have discussed about the chirality, we have discussed about the point groups and symmetry elements. So all of these things have been discussed in this part. Now let us move to the applications of this CD spectroscopy. So in this week's in the last week's lecture, one example of the application of CD spectroscopy was discussed by Professor Arnab Datta, which was for this based cobalt based complex, which has certain amino acids bound to the ligand group. So this is the primary part of this complex, this nitrogen sulfur, which are directly bound to the metal center. So this is the primary structure of this complex. Now this sulfur group is bound to certain amino acids. Okay, and this is what we call secondary structure of this complex. So when this cobalt based complex was left to oxidize, that is left into the oxidation conditions, we observed that metal retained its oxidation state, that is plus 2, but one of the thiolate oxidized, and it was found in square planar geometry. And when this complex was further oxidized, cobalt center got oxidized to plus 3 oxidation state. And and now the geometry of this complex changed from planar structure to octahedral geometry. Okay, so for these complexes, for each of these complexes, before and after oxidation, that is at different steps of the oxidation, we recorded this absorption spectra, and also we recorded a CD spectra corresponding to it. So in the absorption spectra, we observed certain absorption bands. Now the question is, uh, we have amino acids here. What is the part of this complex that is responsible for the absorption bands in this UV visible spectra we have obtained here? So because amino acids absorb in, like, we can say, in the far UV region, but here we can see different bands which are labeled as pi to pi star, DD transition, and LMCT transition. So these bands are originating because of the metal center, cobalt metal center, which is bound to this N2S2 based ligand. So this cobalt metal center is involved in the dd transition and lmct, that is ligand to metal charge transfer, in this particular molecule, particular complex. So here these are the bands we obtained. So now we recorded the optical spectra for this at different pH, but in different pH conditions, we didn't observe any changes in this LMCT band. But in the case of CD spectra, when for the same complex we recorded this CD spectra, we observed. So, for example, we took this oxidized complex at different pH conditions, that is 2, 3, 4, 5, and 6. We see that uh, there is no change observed in this LMCT band, that is ligand to metal charge transfer band. However, there was some change observed in this pi to pi star and this dd transition. Sorry, dd transition is in higher wavelength region. So there was no change observed in this LMCT band in the optical spectra. But for the same complexes, when we were recording the CD spectra, we observed that certain bands uh, are diminishing and some new bands are formed in this CD spectra. But how do we get this change in the CD spectra? The CD spectra is showing the change because of this amino acid which is bound through this sulfur center, and this amino acid is inducing chirality in this complex. That is what we call induced chirality, and because of this induced chirality, we are observing a difference in the a difference in this complex at different pH conditions. But why do we observe a change in this case we observed more change in this pH 3 to 4 region? Because in the weakly acidic region, because in this pH 3 to 4 region, which is which for which this pK of COH is matching, this OH this OH group is not OH function OH group is not getting deprotonated, and this is uh, introducing proton relay, and because of which, oh god, this one is different, sorry. Okay, I'm sorry for this confusion. So I was discussing about this thiolate. This thiolate example, but this image I have attached here is for this is for this cobalt selene example. So I'll erase it again. I'm sorry about this. So this example, which we discussed recently, so this was for this cobalt selene complex. When this salicylaldehyde react with the primary amine in these reaction conditions, it forms a selene ligand. This imine bond is formed by reaction of this carbonyl and primary amine to give us a selene ligand. And when this selene ligand undergoes metallation with cobalt salt, it gives us this cobalt selene complex. This is cobalt selen complex, and R here is amino acid, aromatic amino acids. Benzylamine, so this benzylamine is just an aromatic group, and then we took some aromatic acids, aromatic amino acids, sorry, and pKa for this COH is 3 to 4. We also took tyramine. And this tyrosine. So one we took just an amine and then an amino acid based group. Again, this is tyramine, and based on this, an amino acid was taken, which is tyrosine. So because of metal center, because of cobalt metal center bound to ligand, selen ligand, we get absorption bands in optical spectra. So we took four complexes: C1, which was based on benzylamine R group, and C2 is based on this phenylalanine amino acid. C3 is based on tyramine, and then C4 is based on tyrosine amino acid. So we took a amino acid based complex, which is C4. That is, we took tyrosine, and we recorded the optical spectra for it at different pH conditions, right from pH 2 to pH 6. So we observed that there is no change in the there is or we can say there is no significant change in the LMCT band under different pH conditions. But for the same complex, we recorded the CD spectra under these different pH conditions. So, corresponding to this pi to pi star band, we got a band in the same region. But in this part, in this LMCT region, we observed new bands in CD spectra were observed in same wavelength region as LMCT band in optical spectra. Now we understand that we are getting a band in the optical spectra because of DD transition and LMCT transition. But how did we get how did we get these bands in the CD spectra, and that too we are observing some changes in these bands in different pH conditions. And this happened because in this C4 complex, the R group is tyrosine amino acid, and this tyrosine amino acid is chiral in nature. So it introduces chirality in the complex, and because of this, the molecule is CD active. Now, in different pH conditions, so the COH group has a pKa of 3 to 4. So in the pH region of 3 to 4, you will see that this OH group is not getting deprotonated, and because of that, it is involved in the proton relay. That is, it is like it is promoting the proton relay to the metal center, and hence it is increasing the electrocatalytic hydrogen production. So we were basically doing electrochemical hydrogen production with this cobalt based complex, and we were looking into how this complex behaves under different pH conditions, in which pH conditions we are getting high hydrogen production activity. So in this pH region of 3 to 4, we got uh, we got enhanced hydrogen production activity of this cobalt based complex. So as you can see, in pH conditions above 4, this since the pKa of COH is 3 to 4, so we see that this COH bond was not was deprotonated in the pH conditions above 4. So this O minus group was internally bound to this cobalt metal center, as you can see here. So this OH group was deprotonated in pH greater than 4 conditions and internally bind binds with the metal center. But on increasing the acidity, that is below pH 4, which is the same reason for pK of COH is 3 to 4. That means COH is not getting deprotonated here, deprotonated, and it will involve in proton relay, resulting in enhanced hydrogen production activity. So this is the example hydrogen production activity, and we could observe this change because of induced chirality. So the complex was not chiral if we were taking benzyl amine and this tyramine only, but in the case when we took phenylalanine and tyrosine amino acids, which are chiral amino acids, they induces chirality in this complex, and because of it we can record a CD spectra. Now the complex is CD active, and we can study the changes in the complex due to different pH conditions. Reduce chirality because of amino acid. And the third example was discussed, that was quadruplex, guanine quadruplex. So this is guanine. So this is guanine amino acid, and we know it is present in the double helix structure of the DNA, where it bonds with the like adenine binds well with the thymine, and guanine binds with the cytosine to form the double helix structure of the DNA. So this guanine binds together with hydrogen bonding to form a hydrogen bonding based network, which is a tetradentate network. So here you can see there are four guanine moieties which are bound to each other through hydrogen bonding, to form a tetradentate ligand form, and this is what we call, it is called guanine quadruplex. And this metal center is generally sodium potassium. And this guanine quadruplex, it is formed in parts with guanine rich sequence of DNA. So the parts of DNA where this guanine is found predominantly, there we can find this guanine quadruplex. And this and the reason where this guanine is and this guanine rich reason is found in terminal segment of chromosomes, and these chromosomes are called telomere. Telomere. And the significance of this telomere part of DNA is, which constitutes this guanine quadruplex region. So guanine quadruplex stabilizes stabilizes the telomere sequence because it is the point it is the part which is mainly affected by the external environment. External environment. So if this telomere will be affected by any change in pH or temperature conditions of the DNA, so this is where this guanine quadruplex uh, comes into account, where this will be stabilizing this telomere sequence so that it remains like less affected from the external environment, and that is the importance of this guanine quadruplex. But and this guanine quadruplex is like each guanine quadruplex forms a sheet type of structure, like a this G quadruplex is forming a network. So see, this is one thymine, uh, sorry, this is one guanine, second guanine, fourth guanine, and these are bound through hydrogen bonding network. And this is the metal center. So each of the G quadruplex is forming a network, and it is forming network in three different ways. One is parallel. See, this arrow is parallel to each other. And in the case of anti-parallel, it is moving anti-parallel to each other and giving a chair and basket type structure. And in the hybrid part, if you see, these are moving parallel in one part and anti-parallel in one part. So here this shows that it will consist of both the parallel and anti-parallel part. But how are you going to differentiate between these two structures of G quadruplex? So for that, we will record the CD spectrum, because we know this guanine amino acid. What we are taking here is chiral. Uh, okay. Hey Rituparna.
Yes, ma'am.
Actually, I wanted to ask a question. Like from the last few lectures, there are no students joining this interactive session. So, are you getting the notification for the lecture?
एक्चुअली मैम ये हमारे एसएमएस में अभी आया
Yeah. Okay.
एंड ईमेल में आया था एक बार फिर और एक बार नहीं आया तो आई डोंट थिंक
Okay. So, are you following these lectures or not? Like on the YouTube channel, or because uh, I was thinking why no one is joining, and this way it is not helping me and anyone else. Then, so do you have any doubts?
यस मैम एज बिकॉज मैम मैंने भी ये क्लास किया है जो इंटरेक्टिव क्लास फंडामेंटल ऑफ प्रोटीन केमिस्ट्री तो मैम जो भी वो क्वेश्चन डिस्कशन किए हैं जब वो आता था जो असाइनमेंट में हम वही क्वेश्चन का आंसर अगर लिखते थे तो आंसर रॉन्ग हो जाता था तो पता नहीं ऐसा क्यों बट पर्टिकुलर क्वेश्चन था जिसका आंसर रॉन्ग आया था जहाँ की इस क्लास में बताया गया था कि वो आंसर करेक्ट है तो इसीलिए हम थोड़ा
Okay, like which was, can you tell me the question?
1 मिनट
So in the
कैन आई सर्च मैम फॉर
yes,
मैम 1 मिनट आई वांट टू सर्च
okay. So in the interactive session, it was taught wrong. That's why your answer got incorrect.
यस मैम
Oh, I'm sorry about it, but can you tell me the question? Then only I'll be able to help you.
यस मैम
What was the topic of that question? Can you tell me?
Yes, ma'am. I'm 1 minute, ma'am. I'm just
Okay, okay, fine. Take your time.
searching it.
Okay, take your time.
Ma'am, that is a question that assignment number week 4, assignment 4,
Okay.
question number 2.
Assignment 4.
Question number 2.
Yes, yes. Suppose a solution contains 90 milligram of glucose mixture. If it contains 54 mg of
No, ma'am. No, ma'am. No, ma'am. That is not, ma'am.
okay,
Ma'am, this is written during a successful purification scheme. It may be expected that one में लिखा है specific active activity increases, टू में लिखा है specific activity decreases, थ्री में लिखा है number of protein in the sample decreases.
I'm looking in the week 4's assignment. So assignment 4 is that one, na? I think you are referring to other assignment.
Yes, ma'am. मैम वीक 4 असाइनमेंट 4 में हमारा जो फंडामेंटल ऑफ प्रोटीन केमिस्ट्री में ये मैम ये फंडामेंटल ऑफ प्रोटीन केमिस्ट्री तो सही होना चाहिए.
Yes. आप आपने दूसरे कोर्स का ये तो नहीं ज्वाइन किया है फंडा, बिकॉज कोर्स का नाम सीडी सर्कुलर डाइक्रोइज्म एंड मोसबियर स्पेक्ट्रोस्कोपी है. एंड बिकॉज मैं असाइनमेंट असाइनमेंट 4 का जो क्वेश्चन है वो मैच नहीं हो रहा आपके क्वेश्चन से.
मैम 1 मिनट मैम.
ओके, नो प्रॉब्लम.
मैम एक्चुअली वीक 4 में हमारा जो लेक्चर है उसमें है प्रोटीन आइसोलेशन मेथड, प्रोटीन प्यूरिफिकेशन, बायोफिजिकल मेथड 1, बायोफिजिकल मेथड 2, बायोफिजिकल मेथड. मैम कोर्स का नाम क्या है?
कोर्स का नाम है सर्कुलर डाइक्रोइज्म एंड मोसबियर स्पेक्ट्रोस्कोपी.
तो सॉरी मैम. मैं मैम आई एम सो सॉरी.
ओके, नो प्रॉब्लम. आपने इस कोर्स
ये
को
एक
रजिस्टर किया
मिस्टेक
है?
हो फंडामेंटल ऑफ बायोकेमिस्ट्री सॉरी प्रोटीन केमिस्ट्री में रजिस्टर की हूँ एंड मैंने शायद गलती से ये इसमें ज्वाइन कर दी.
ओके, नो प्रॉब्लम, नो प्रॉब्लम.
मैम आपके साथ हम कैसे कांटेक्ट हो सकते हैं, मतलब अगर कुछ क्वेश्चन आंसर पूछना हो तो कुछ तो
आप
कैसे
ये
हम डायरेक्टली कांटेक्ट कर
ओके,
सकते हैं?
आप ये सर्कुलर डाइक्रोइज्म एंड मोसबियर स्पेक्ट्रोस्कोपी के लिए रजिस्टर करे हो?
नहीं मैम.
नहीं किया है ना? तो बिकॉज आई एम टीचिंग दिस कोर्स, आई एम लाइक टेकिंग डाउट्स फॉर दिस कोर्स सर्कुलर डाइक्रोइज्म एंड फंडामेंटल्स ऑफ बायोकेमिस्ट्री. आई एम नॉट लाइक आई एम नॉट टीचिंग.
ओके.
आप उसका जो टीए है ना, आप
सॉरी
एक
मैम,
बार
सॉरी.
उनसे उनका लेक्चर फॉलो कीजिए. ओके.
जी जी जी. थैंक
ओके,
यू मैम.
थैंक यू,
सॉरी
थैंक
फॉर मिसअंडरस्टैंडिंग.
यू, नो प्रॉब्लम. Okay, so let's continue our lecture. Sorry for the interruption. So, for these three type of structures of this guanine quadruplex, we will get different bands in the CD spectra. For example, for the parallel, we get two bands, one in the positive side and one in the negative, and you can follow it like this. And if you are given a sample of this guanine quadruplex, and you are recording the CD spectra. So if you see the bands in the CD spectra and you match those bands with the reported bands of the guanine quadruplex, you will be able to find out whether it is of parallel or anti-parallel type, or it is hybrid of both. So here, if you see, we have two bands in the positive side and one band in the negative side. So three bands we are getting in the hybrid structure and anti-parallel structure. But we will look into the pattern of this. That is, we will get one positive, then one negative, and then again one positive. So this is matching with the anti-parallel. Okay. Now, uh, if this so this is the this guanine quadruplex was taken in different buffer conditions here. G quad, quadruplex was taken in different pH in different buffer conditions and CD spectra was recorded. So now we have to identify which structure of G quadruplex is present in that buffer condition. So here we see there are two bands. First is negative and then second is positive. So it is matching with the parallel structure. So we assign it parallel. Then similarly in that this TK buffer we are getting similar two bands. So this is also parallel structure of G quadruplex. So these three are parallel. Then in this tris something buffer we are getting one negative band. So here we are getting one negative band and then two positive bands which appear as like shoulder bands of each other. So we can say that this is a hybrid of parallel and anti-parallel. So by matching the obtained spectra in the unknown sample with the reported CD spectra of a particular structure of a sample, then we can find out which type of structure is present in that unknown sample. So I think this was it for circular dichroism. We have covered like the basics of the CD spectra, CD spectroscopy and its applications also. So most of the things have been covered by now. So I'm just summarizing the solutions for these four examples since there are still 15 minutes left. Applications. So I would like to mention this thing. Sometime, we are teaching, like no students are present in these sessions, and these are going very spontaneously. So sometime I might have mistaken on some part, but in overall lecture I have made sure that right uh, right content is delivered. So please follow the complete lectures, and if you have any doubts or I have mistaken in some part of the lecture, then you can write anytime in the discussion forum, or you can write on my mail address, which is tanukoshik29 at the rate gmail.com. So I'll try to help you in as much as possible. So please follow these lectures. Oxidation of thiolate. Oxidation of metal center, like change in oxidation state of the metal center. In this case, we get octahedral geometry. So, in the case of this cobalt based uh, complex, CD spectroscopy able to detect the change in primary structure, metal center is not chiral itself, but presence of chiral amino acids in the ligand induces chirality, and hence it was CD spectroscopy active. Second was cobalt selen complex, in which we looked into how the complex with amino acids as the R group was CD active, and because of that CD activity, that is chirality in the complex, because of the chiral amino acid, we could observe the changes uh, in the complex under different pH conditions. So see how chirality is helping you in studying the different properties of a complex. For example, in this case, you were looking into the hydrogen production, electrochemical hydrogen production activity of this complex. But in the optical spectra, you couldn't observe significant changes in the different bands on changing the pH of the on changing pH conditions. But because of the chirality of this complex, this molecule was circular dichroism spectroscopically active, and we could record its spectra in the CD. And there, with the change in the pH, some new bands were appearing and some bands were diminishing. So this is where chirality in a complex, and hence the circular dichroism, helps you with different studies. Third example was of guanine quadruplex, which we discussed just now. So where we could determine the parallel anti-parallel hybrid structure of this G quadruplex, which is present in the telomere part of the chromosomes. It is found in chromosomes and in telomere region. G quadruplex stabilizes this telomere region, and it it is of different types: parallel, anti-parallel, and hybrid. So you can determine the structure in CD spectra. Okay, so this was it for today. I hope these lectures are helpful for you, and you guys are, at least even one of you is following these lectures. Then I will be happy that it is helping any of you. So thank you very much, and please write your doubts in the discussion forum, or you can also mail me on my email address tanukaushik29 @gmail.com. Um, so okay, thank you so much.